Now let us take up a simple example here. For this program, we try to generate the object code. There is not much logic involved here. You can see that every source statement can have three parts. The three parts are: it can have an optional label, it should have a mnemonic, and an operand on which you are trying to perform the operation. This is the operation that we are intended to perform on what value. Normally this operand will be memory. Normally that operand will be memory resident. Operand is residing in memory. Okay. So WRREC is a label. Start is a assembler directive. It states that we are starting our assembler program right here, and this number here represented in hexadecimal states that your program starts at this address 105D. Then we know this instruction LDR 0 means we are loading constant value 0. I have defined it as constant integer 0. I am loading it to index register. Then length I have defined it as reserve byte 2, which we are loading to T register. And here is an actual output operation we are trying to perform. We will check the output device. I hope you remember TD instruction. It will test the device and it will set the condition code. Two values: less than or equals. Less than means device is ready, equals means device is not ready. So if device is not ready, we cannot proceed to perform the read or write operation, in which case we will loop back and we will test the device again until the device becomes ready. If device is ready, then what we are going to do is we are taking up a character from the buffer, we are loading it into the accumulators rightmost 8 bits. That data we are writing back to the output device. Output, it is a device name. I hope you remember all the input output devices will have a unique 8-bit code that recognizes them. Here I have defined output with the unique code 05. So whatever character we are copying from the buffer, we are writing it onto the output device called as output. And after writing 1 byte of data to the output device, we are incrementing the index register value by one TIX instruction. What is the job of TIX instruction? It will increment the value of x by 1. Also, it will perform the comparison on length. And if index register value has not reached the buffer length, maximum buffer length, which we have not defined, we have just reserved 2 bytes. Any value you can fill up in this 2 bytes of memory. So until we are reaching the end of the buffer, we are repeating the same set of operation: testing the device, loading the character from the buffer, and sending that copied character from accumulator to the output device. We are repeating these steps again and again until we are running out of the data in the buffer. So this is a simple program. We have chosen this program to learn the object code conversion in SIC. And I told you the job of assembler here we have seen. The job of assembler is to convert mnemonic operation code to their machine language equivalent. And here is a table which represents the mnemonic operation code and its associated opcode in SIC. In the Leland-Elbeck textbook, in the appendix, you can find all the instructions supported by both SIC and SIC-XC machines and its equivalent opcode, how operand address should be calculated. All the details relating to this can be found in that appendix, but I have copied few of them which I require for this program here in this slide for our use. If the mnemonic is LDX, if the mnemonic is LDX, its equivalent opcode is 04. So wherever the assembler sees the instruction LDX, it will replace this LDX with the value 04. Fine. LDT is 74, TD is E0, JEQ is 30. Likewise, you can find the list here. These are all only the instructions which I have used in my program. Next, now we know that we can easily convert the mnemonic to machine code. Next step is convert symbolic operands to their equivalent machine address. That means what is the address of 0? What is the address of 0? See, we have an instruction here. What is the first instruction? I told you start is an assembler directive, and assembler directives are not converted into object code. So this is not our first instruction that will be converted. Instead, we are converting the next instruction, which is LDX 0. And how to convert LDX? Already we know that mnemonic and its equivalent opcode. Wherever LDX is there, 04 will be replaced. And also the second step is we have to convert the symbolic operand to their equivalent machine address. So 0 has to be converted to its address. Where do I find the definition of 0? 0 is present at line number 60. The line numbers are for just reference. They are not part of the program. See, I want to know the address of 0 here so that I can convert this entire instruction. What is the instruction? I write here again. LDX 0 is the instruction. This one I have to convert it into machine language, which contains only zeros and ones. LDX is 04. Now I need to know the address of this 0. But where is the 0 defined in our program? It is defined at line number 60, where I am requiring the address of this 0 at line number 10. This problem is called as forward reference. Forward reference. What do you mean by forward reference? You are referring to a label which is defined later in your program. At this point of time, while the assembler is processing line number 10, assembler is not knowing the address of the 0. It is not knowing the address of any of the labels here. This problem is called forward reference. And to solve the forward reference problem, most of the assembler will do two passes. In the first pass, it will just scan the source program for all the label definitions and it will assign addresses for each line of the code. Normally, it will assign addresses to all the labels. But we will assign addresses to all lines of our code, which is easier to process. And in the second pass, it will perform the actual translation job. I repeat the forward reference problem again. Please see here. We have, for example, LDT length. I want to convert LDT length to machine code. What is the opcode equivalent of LDT? LDT is 74. What is the address of length? I don't know because it is defined later in the program. If assembler is processing line number 15, it is not having any information regarding the label definition which appears at line number 70, right? So it doesn't know the address of the length right now. This problem is called as forward reference. And how to solve the forward reference? To solve the forward reference, most of the assembler will have two passes. In the first pass, what it will do, it will just scan the source program and it will look for all the label definitions. And for all the label definitions, it will assign the address. Now, you know all the labels present in your program with its associated addresses. And in the second pass, it can perform the actual translation. Now, coming back to the program, what is the first job now? First job is first pass. What is pass 1? We have to assign addresses to all the labels in our program. We not only assign addresses to all labels in our program, instead we assign address to each line of our program. How can we assign address to each line of our program? It is very, very simple. If you remember, in SIC all instructions are of equal length, right? In SIC all instructions are of equal length and they are 3 bytes in size. So what is the address of the first instruction they have given? The first instruction starts at 105D. 105D. Wait a second. Does start is actual instruction? No, it is a pseudo instruction. It is an assembler directive. So we have to proceed and my first instruction will appear at the address 105D. Right? What is the instruction? LDX 0. Then where do my second instruction appear in the memory? It will appear after 3 bytes because LDX 0 is one instruction which occupies 3 bytes. After 3 bytes you can load the second instruction. After 3 means I have 105D. Where will my next instruction appear? Where will my next instruction appear? 105D plus 3. You can use the calculator. You can use the calculator and add 3. I know this is very simple calculation, but still we will use this once because it involves hexadecimal computation. Most of the times students make mistake while adding, right? So we will make use of calculator. 105D plus 3 is 1060. 1060. Similarly, LDT again occupies 3 bytes, so my next instruction will appear at 1063. Next instruction will appear at 1066. Next instruction at 1069. After that, my next instruction will appear at 69. After 9, it is 6A, 6B, 6C, right? 6C. Next instruction will appear at 106. D, E, F, 6F. And next instruction will appear at 10. F. After F, what is the next number? It will be 10. But now we have 6 already behind F. So it will be 7, 70, 71, 72. So this will be my next address. And after 1072, it is 3 bytes again from 7072 is 7075. And afterwards again R sub occupies 3 bytes. 75 plus 3 is 78. What is the next address? What is the next address? See, what is the instruction? It is output byte hexadecimal 05. How many bytes are we occupying here? Only 1 byte. I have defined only 1 byte of data here. Hexadecimal 05 consumes only 1 byte. So I have to add only 1 after this 1078 because this output, it is a memory location which is occupying only how many bytes? How many hexadecimal values we have defined here? Only one constant hexadecimal value which occupies only 1 byte. So my next address will be 1079. Now calculate the next address. How to calculate the next address? What is the next data? We are having 0, word, 0. Word means how many words are we defining here? Only one word. One word means 3 bytes. So again I have to add 3 to 1079. If I add 1079 with 3, I will get 7ABC, 107C, right? Now after 107C, what will be the next address? How to compute the next address? We need to see how much memory is occupied by this buffer. What is buffer? It is reserve byte. We are reserving few bytes. How many number of bytes? We are reserving 400 bytes. 400 in decimal we are specifying there. We need to see what is its value in hexadecimal. Right, I will clear this. 400, I want to know in decimal if it is 400. What is its equivalent in hexadecimal? It is 190. Sorry, it is 190. So what is my previous address? Previous address is 107C. That has to be added with 107C. Should be added with 190 in hexadecimal, which is 400's equivalent, right? If we add this, we will get the address. Oh, I forgot the address. What is it? 120C. 120 C is the address. 120C is the address, right? Next, how many bytes does this length occupy? We are reserving 2 bytes. So the next address would be 120DE. 120E, 2 bytes, right? But end is an assembler directive. It is not anyway converted into object code, so we don't have to assign the address for the end. Okay, this is how addresses are assigned to each line of our code. Okay, after assigning the addresses, now our job is very simple. What we can do is we can copy this table into our screen there. Okay, now we can fill in the object code. It is very easy now. Once we know the address, once we know the opcode of all the mnemonics, we can easily convert each instruction into its equivalent machine code. Do we have to convert the line at number 5? No need, because start is an assembler directive, so it will not have an equivalent machine code. So I can skip this line. Let's go to line number 10. What is the instruction? LDX. For LDX, what is the opcode? Opcode is 04. And what is the operand we are having? 0. What is the address of 0? Where you can locate 0 here. 0 definition. 0 definition, you can find it at the line number 60. What is it? What is its address? It is 1079. So it is just 1079. This is the equivalent opcode for the instruction LDX0. So assembler has converted English looking like statement LDX0 into its equivalent machine code, which is in binary. No ma'am, 0, 4, 1, 7, 9, or they all binary numbers. They are represented in hexadecimal, which is direct representation of the binary numbers, right? Then let us do the next one. Let us take up the instruction at line number 15. Mnemonic is LDT. Its equivalent opcode is 74. So take 74 here. Find the address of the length. Length is defined at the address 120C. Length is defined at the address 120C. So LDT length is equivalent to 74120C. Next instruction is W loop TD output. What is the mnemonic? TD. What is its equivalent opcode? E0. Output. Locate the label definition output. It is at the address 1078. So attach it here, 1078. Next instruction is JEQ W loop. JEQ equivalent opcode is 30. W loop is found at the address 1063. Here it is. W loop is present here, right? Then next instruction is LDCH buffer comma X. This requires little explanation. Can you identify the addressing mode now? What is the addressing mode? What is the addressing mode? Comma X is there. In SIC we have two addressing modes, direct addressing mode and indexed addressing mode. And this is an example of indexed addressing mode, right? So if it is indexed addressing mode, how the instruction will look like? We have the instruction format something like this. We have 8 bits of opcode, 1 X bit, and then we have 15-bit displacement. 15-bit address, sorry, not displacement, it is address, right? So what is 8 bits of opcode? LDCH is the instruction. Its 8-bit opcode is 50. 8 bits opcode is 50. And comma X is there. That indicates that this is an indexed mode, indexed addressing mode. When we have indexed addressing mode, X bit will be 1. And what is 15-bit address? The address of buffer we need to find. What is address of buffer? It is 107C. 107C. So now we have to, how to compute the target address now? We have to add the target register, X register contents plus the displacement to find the actual address. Now what we have to do is, what we have to do is just convert this into object code. That is sufficient. That is sufficient. How to convert this into object code? Let me write this value in binary. You will understand. This is 0, 0, 1, 0, 0, 0, 0, 0, 1, 1, 1. C is 1, 1, 0, 0. And we have 1 here. And 50 is the opcode. This is already in hexadecimal. This one I am writing as it is. This 15-bit address, which is 10717C, I have expanded into binary. Now I have to combine 4 bits and I have to convert it into hexadecimal. Right? So 50 is already there. 1001 will be 9 and 4 number of zeros will be 4. This is 7. This is C. This is C. Understood? Whenever there is a indexed addressing mode, which is denoted as comma X in our instruction itself in SIC. So whenever there is indexed addressing mode, X bit will be enabled. It will be 1 and remaining 15-bit address we will have it. So we have to combine this 1 with this 3-bit binary number here. When we do that, we are getting 9 in this example. So what is the object code corresponding to this? The object code corresponding to this is, so what is this value? LDCH is 50 and 90 buffer, we can find it address 107C. I have combined it with the index register contents, sorry, the index bit in the instruction. Next is WD output. WD is DC and output definition we can find at the address 1078. 1078. Next is TIX length. TIX, its equivalent of code is 2C and length definition we can find at the address 102C. Next is JLT W loop. JLT is 38 and W loop is 1063. Right? R sub is 4C followed by 4 zeros. R sub is not having any operand. R sub is not having any operand. What is R sub instruction? Return subroutine. Return to the called subroutine. How you can go back to the called subroutine? You just have to pick up the return address from the link register and make a jump to that address. Right? You don't have to specify any operand here because the return address is already been saved in the link register whenever you are making use of JSub instruction. Anyway, we are not using JSub here, just an RSub instruction. Right? Now comes the next part. Let's go back to our earlier slide. You can see here we have converted all symbolic operands to their equivalent machine address. We have decided the proper instruction format for all the instructions, and we have also converted all machine opcodes to the machine language equivalents. We need to convert the data constants to their internal machine representation. This is remaining now. This now we are going to do, right? All hexadecimal value we are having, hexadecimal constant we are having in our program. How constants are represented in the machine? Binary value. Already we are having the binary value itself, so we can use it directly. Please note, hexadecimal representation is a direct form of writing a binary number. Each digit you can pick up from this hexadecimal value, convert it into binary by just writing their 4-digit equivalent binaries. That's it. Right? Now what is the next value we are having? We are defining an integer constant 0. Integer constant represented in binary in 24 bits. I have done it in hexadecimal 000000. Now, do we have to write anything for reserve byte? No need. No need. Only if constants are there, then we have to write their machine language equivalents. But whenever we have reserve byte or reserve word, they need not be converted into opcode because these lines are not at all converted by the assembler itself into their equivalent machine code, right? Assembler directives are not processed, correct? But here we are defining a constant. That constant value we have to convert it into machine representation. How they are internally going to store in the machine, that has to be represented while we are defining the constants. But here we are not defining any constant, we are just reserving the space, so it need not be converted into object code, right? And this is end of our program. So finally, we have converted each line of our program into its machine language equivalent. Object code we have created for our entire program. If you remember, the assembler, it generates two output. One is object listing and another one is object listing and object program. These are two outputs of our assembler, any assembler. So what we have generated now is an object listing. This is object listing. This itself we call it as object listing. So coming to the object program, we have a specific format for writing the object program. This is the reference of the page number from the textbook Leland, Elbeck and Manjula. So now any object program will have, any object program in SIC, it will have these many kinds of records included in it. The first kind of record is header record, followed by text record, followed by end record. What is header record? What does it contain? Column number 1 will have H to indicate that it is a header record. Column number 2 to 7 will contain the program name. Column number 8 to 13 will have starting address of the object program. After you have converted your program into object code, you also have to specify the starting address. In our program, you might have seen the starting address is 105T. That address has to be mentioned, and you also have to calculate length of the object program in bytes. That also has to be included in the header record. How to compute length of the object program? It is very simple. Just find the last address of your program minus the first address of our program. So for this example, what is the last address? What is the last address? It is 102C, which occupies 2 bytes. So our last address will be 102C plus 2. 102C is already there. I'll just add 2 to it, which will be equal to 102E minus the starting address we have to do. What is the starting address? It is 105D. We get 1B1. So this is the length of our object code. Okay, now coming back, I hope all of you understood what is header record. Since I have moved back and forth between the slides, I summarize again. The header record will contain H to the beginning, and followed by program name, which is WRREC in our example, followed by starting address of the object program, which is 105D, and also we have to specify length of the object program in bytes, which is 191, right? Sorry, 1B1. Next is the format of a text record. Text records will start with T, and then we have to write the starting address for object code in this record. Please note that maximum length of the text record will be 1E. It can occupy 1E number of bytes. It can accommodate 1E number of bytes or lesser as well. Okay, so we have to specify how much of the object code are we going to accommodate in this particular record, and that number will be represented in hexadecimal. Please note all the numbers in our object program is going to be in hexadecimal itself. Need not to explicitly mention again and again. Followed by the object code, and we are representing 2 columns per byte. I repeat, the text records will start with T, followed by starting address for this particular record of an object code, followed by length of the object code in this record, and maximum length that we can accommodate in one text record is 1e number of bytes. You can accommodate only 1e number of bytes in one text record. So if you are having a bigger program, then we are going to have multiple text records, each containing 1e number of bytes. And maybe our last text record may not have 1e number of bytes, in which case it will be lesser than 1e number of byte. So for each text record, it is mandatory to include the length of the object code in that particular record, and it is measured in bytes. And finally, we will write the actual object code itself. Okay, and the last format, the last record type of the object program is going to be the end record. It starts with E, and it should be followed by address of the first executable instruction in the object program. Okay. And to separate the fields, we are going to use this caret symbol in between. For example, if it is a text record, I will write like this: H caret, program name is WRREC caret. Starting address of my object program is going to be 00105D caret. Length of the object program will be 0001B1. 14 to 19 means it is 6 digits there. I'm making the length 6 digits long by appending zeros, not changing the values, and we have to write like this. Okay, now I will give the complete object program for the program we have just converted into object code. Header record, name of the program, starting address, length of the program. First text record starts at the address 105D, total length, I will come to this later, followed by actual object code itself. Let's go back to this slide. You will understand how to write the text record. The text records will be written like this. It starts with T, followed by where does this text record start. First instruction will appear at 105D, so it will be 00105D. Maximum length will be 1E. I will leave this blank for time being because I don't know my entire program fits in 1E bytes or not, or it may exceed also. We don't know yet, so I will leave it blank, but keep it in mind it should be equal to or less than 1E. Followed by actual object code. What is the first object code? First object code is 041079. 041079. Next object code 74120C. 2 columns, 1 byte. So how many bytes I have occupied already? 3 bytes here, 3 bytes here. Next, what is the next object code we are having? It is E01078, followed by 301063, followed by 50907C, followed by DC1078, followed by 2C, it is 2C120C. Are you getting? Followed by 381063. Now let us count how many bytes already we have used. 3 plus 3 6 plus 3 9, 9 plus 3 is C, C plus 3 is DEF. For up to here we have used F number of bytes. F plus 3, 101112. Here we have up to here it is 12, and plus 3 is 15, plus 3 is 18. Then that means we can accommodate more. Next one is 4C, followed by 4 number of zeros. Now it is 19, 1A, 1B. Up to here I have used 1B number of bytes. What is the maximum limit? Maximum limit is 1E. So what is the next value we have? 05. When I say 05, I have occupied 1C number of bytes. Have we counted properly? D, E, F. That means I can, F I cannot accommodate, right? So up to 1C I can accommodate here. If I have to include the next value also in this text record, will it accommodate? Already I have used 1C number of bytes. Next data is consuming 3 number of bytes. When it is 3 number of bytes, 1D, 1E, 1F, that means I will exceed the maximum limit of this text record. So I have to stop right here and I will write the maximum length of this text record is 1C bytes. And I have to stop this text record. And now again I have to start the new text record. I don't have space here, I will show here. See, up to 1C I have done here, and I have to start the new text record. The format will be same, text record followed by the starting address of the instruction for this record. Where is this instruction appearing? See, up to 1078 already I have included in my previous text record. My next instruction that should be accommodated in my new text record will appear at the address 1079. Right, it will appear at 1079. So I have used the starting address of this text record starting at 1079, and length is 03, and I have not written the object code here. Sorry for the inconvenience. The object code itself is constant value 000000. Right? This is end of text record. After end of text record, these are the only instructions that are my program is containing, right? And finally we have the end record. What is the format of end record? It will start with E. It will have address of the first executable instruction in the object program. It will have E and start of the first executable instruction at the address 105D. I just have to write the address of the first instruction. This is format of the object program. So now we have seen the object program as well as object listing. Which are two forms of outputs of any SIC assembler. Thank you.